Ready to give the talk? Good. So this is about a relational solver for Java generics type system, and work is done at St. Petersburg State University, and Petr Lozov will give the talk. So please go ahead.
Hi. Can you hear me? Okay. Hello, my name is Petr Lozov. Unfortunately, we were unable to attend in person, so there will be a virtual speech. Sorry, I need to switch off my headphones. I hear myself. Today we will talk about relational programming and its application to solve Java generic type system inequalities. Well, first of all, we will talk about the motivation behind this problem. As you know, the Java language is one of the popular high-level and object-oriented programming languages. Currently, approaches to verification and automatic testing of Java code are being actively researched. And one of the prominent methods for software testing is symbolic execution. A crucial component of the symbolic execution engine is the type solver. The solver is necessary to check various type constraints. For example, the solver is needed to verify typecasting in code. The solver has to search for all types that satisfy the system of inequalities with free variables, system of type inequalities. In this example, we need to find all types that are subtypes of a list with a specific type parameter, and at the same time, they should be supertypes with any type parameter. Java generic type system is complex enough that the subtyping relation is undecidable, and direct implementation of the solver is a non-trivial task. At the same time, the verifier of subtyping can be implemented directly according to the Java language specification. This is great news because relational programming will allow the verifier to be used as a solver. And a bit more about Java type system. In the context of this work, we are dealing with the Java generic type system. This is a standard object-oriented language system that includes classes and interfaces with the ability to inherit for classes and for interfaces too. Although classes and interfaces can have generic parameters with various type constraints, like this. Next, let's talk about relational programming. Relational programming is an approach based on the idea of describing programs as relations. It can be considered as a branch of logic programming, but without all non-relational constructs, such as side effects or extra logical features. Also, it uses interleaving search strategy, which is complete. As a result, all solutions are guaranteed to be found. Conventional relational language is Minicanon. Initially, it was embedded domain-specific language for Scheme and Racket, but then Minicanon was ported to many host languages. In context of this research, we use a strongly typed implementation for a camel called Acandron. Thanks to the completeness of the search and the absence of non-relational constructs, Minicanon allows to express inverse computations. And a lot of complicated programs can be considered as an inversions of simpler programs. For example, the inversion of list sorting is a generator of all permutations for a sorted list. or the inversion of a type inferencer is a type inhabitation solver. In particular, a solver for some problem is the inversion of a solution verifier for this problem. In practice, this is useful because verifiers is often easier to implement than solver. Let's consider a simple but observable example. There are two versions of piano numbers addition. The first one is functional version in a camel. We can use it for addition only. The second one is relational piano numbers addition. Unlike the functional version, the relation program has an extra argument. This argument corresponds to the result of addition. As we can see, both programs have a similar structure. We have two branches. X is 0 and Y is result in the first branch in both cases. And we subtract X and result by 1 and have recursive call in the second branch. And at the same time, the relational version can be used more flexibly. Of course, we can add two numbers, but we can also subtract numbers. This is a simple example of inverse computation. Moreover, we can synthesize all pairs of addition operands whose sum is equal to a given number. We fixed the last argument and we want to find the first and the second argument. As we noted, functional and relational programs are very similar. This is true for many other cases as well. Instead of writing a relational program, we can write a functional one. And then we can convert it using our tool of automatic relational conversion called no-conrun. In practice, an automatically converted program is often not efficient enough. That's why we mix handwritten and converted relational code. Well, we have everything we need to describe our approach to solving subtype inequality systems for generic Java types with free variables. We use relational programming techniques like relational conversion and verifier to solver method in our approach. And to boost performance, we also apply some problem-specific optimizations. Our approach consists of two components: direct subtyping relation and closure of this relation. Let's talk about direct subtyping relation first. We implemented direct subtyping relation in a camel according to Java language specification. This implementation can verify that one type is a direct subclass of another type according to given type class table. Then we generated relational verifier using no-conrun. This verifier, relational verifier, can search for all substitution for free variables in incomplete types to make them subtype of each other. In particular, a relational verifier can synthesize direct subclasses or direct superclasses of a given type. In other words, it's a solver of direct subtyping. We can use relational verifier as a solver. As I said earlier, this solver will be a part of symbolic execution engine. So we excluded some Java language specification components from the implementation to ensure only instantiable classes to appear in answers. Now let's discuss the transitive closure of the subtyping relation. Closure allows to search for all subclasses or superclasses, not only direct. Closure can be expressed in miniconrun directly according to the formal definition of reflexive transitive closure. You can see this definition on the slide. And this relation is easy to express directly in miniconrun without no cannon using conversion, relational conversion using. Yeah. After implementation, we found that the performance of the solver was very low. It took seconds to come up with the first solution, even for small class tables. So we implemented some optimizations to improve performance. First of all, we optimized the ineffective parts of the converted code. For instance, no cannon always converts integers to piano numbers because we need to use piano numbers in relational arithmetic operations. However, class and interface identifiers are not used in arithmetic operations, so piano numbers was replaced with integers manually, and it's improve solver's performance. Then we optimized the evaluation of closure based on the groundness analysis of the arguments. We have two closure implementations for finding subtypes and supertypes. And we dynamically select the optimal version based on argument groundness. Finally, we optimized the search in class table. We dynamically construct the search relation depending on its argument's groundness. Let's look at simplified example. This relation is built on a specific class table, very simple in our case. It connects the identifiers of subclasses and superclasses. If both identifiers are fresh variables, we need to do all these unifications, and it's expensive. But if at least one of the identifiers is ground, we can exclude unification from the relations which are guaranteed to fail. For example, if ID of superclass is 4, then we can exclude 4 disjuncts from relation. Of course, this is a non-relational solution because we change relational program during evaluation. However, we only exclude unsuccessful branches. As a result, the set of answers doesn't change, but efficiently increases. We evaluated our solver for real-world class table containing more than 40,000 classes and interfaces, and we use 9 realistic benchmark queries of various shapes. There are 2 single-type inequalities and 7 different systems of inequalities. First, we wanted to evaluate the effectiveness of the developed optimizations. So we tested 4 versions of the solver without optimizations, with optimized closure, with optimized search in the class table, and with both optimizations. Also, our solver is guaranteed to find all the answers, but it may find the same answers several times. To evaluate the number of duplicates, we calculated the total number of answers and the number of unique answers. Finally, to evaluate effectiveness, we measured 4 time metrics. We represented results of evaluation in the form of a bar chart. Here, the groups of 4 bars correspond to different benchmarks. Each bar in the group corresponds to one of 4 versions of solver, left to right, with no optimizations, with optimized closure, with optimized search in class table, and with both optimizations enabled. Below each group are the number of unique answers and the total number of answers. All measurements are presented in a logarithmic scale. We also limited the evaluation time to 5 minutes. And if in a few cases, we received only a part of the answers. In this case, we indicate the time for calculating the first answer only. For example, here, here, and here. Oh, sorry. Here, here, here. And in few cases, we did not receive a single answer. The red column is shown in the bar chart in this case. For example, here, here, and here. As you can see from the results, closure optimization, the second column, in each group, improves the result by an order of magnitude, but only for some specific cases. And the class table search optimization always improves the result by an order of magnitude, but the best performance is achieved when using both optimizations together. Although the performance of the solver depends on the order of inequalities in the query. The benchmarks 3 and 4, sorry, 4 and 2 and 3, and 8 and 9 only differ only in this aspect. They differ only by order of inequalities. But we can see different evaluation results. Finally, it can be noted that solving the superclass inequalities delivers a large number of duplicates answers. Benchmarks 5, 6, and 7 contains superclass inequalities only if we can see a lot of duplicates. So we can conclude that optimized version of solver show promising performance results, but the performance depends on the order of inequalities and the presence of duplicates. Well, we developed Java generic type solver using relational conversion and verifier to solver techniques. Then we optimized the solver to improve the performance, and we evaluated the solver performance. This is the approach we are currently working on. Moreover, at the moment, the duplicates problem has already been solved after we wrote our paper. We eliminated duplicate search branches to remove duplicate answers and improve performance. Sorry, I'm again here myself. In the future, we plan to research the problem of ordering inequalities and integrate the solver into our symbolic execution engine. And another interesting problem to generalize our solver for negative type inequalities. A solver for such inequalities is also needed for symbolic execution. That's all. Thank you. I'm ready to answer your question.
Okay, Peter, thank you very much.
Oh, I hear you, but with echo. Maybe I need to switch off my micro. I'm not sure.
We have time for questions,
Yeah.
or are there any questions? So maybe I have a question. So in Minikenran, there is also support for different search strategy. You showed us only how to optimize the subtyping tables. Have you also tried other search strategy, or was it the standard complete, only the standard complete search strategy of Minikenran?
Yeah, thank you for question. Of course, we need to use a complete search strategy because we need to find all answers. But indeed, we have a lot of different complete search strategies. Yeah. But when Minikenran was developed, mini-canon authors tested a lot of different strategies, and interleaving search was show the best performance than each other.
Mm.
So we don't testing other search strategies, and maybe it will be interesting research topic for us. Yeah, thank you.
Yeah, yeah. Okay, Robert.
Hello, Peter. Thank you for your interesting talk. I have a question regarding how much do you think it will be scalable up? I think at the beginning you mentioned you have taken a subsystem of the generic type system. Would it be possible to extend it to the entire specification? How is your feeling?
Yeah, thank you for the question. I think this system is scalable because we just repeat semantic of subtype relation. If we have if we want to extend subtype relation, we can just extend functional implementation of this semantic. Then we can translate it, etc. Now our Java type subsystem already contains generic types, generic interfaces, arrays, type variables, intersection types, etc. Yeah. Thank you.
Okay. So I do not see any more questions. So thanks again for your talk.
Thank you.